Today you're going to start the second half of the fields unit, and instead of gravitational fields we're going to deal with electric fields. And one thing I want to say right off the bat is when you do electric field calculations, there's usually diagrams with them, and the diagrams tend to look scary. I mean, we don't usually get a lot of diagrams in our questions up until now. But you will start to see diagrams, and don't get worried by what the diagrams look like. They're actually there to make things as easy as possible. So today's sheets, make sure you print them off first. We're going to go through one example question, and this is not a typical example. This is probably it's a more difficult example because it covers everything. So I'd like to go through this example because it covers the entire set of calculations. And then there's 4 homework questions today that are much easier than this question. So don't watch this video and think, oh my gosh, how am I going to do 4 questions like this? On the other hand, this is not a difficult question. I shouldn't have said it was hard. It's complicated because it goes through everything, but I think you're going to find it very sensible and very easy. But we need a few things first. One of the things I will say about electric fields, if you remember before class ended, I said that the electric field work was going to be a little bit more difficult. One of the reasons is when you have a series of particles like this in one question, the forces aren't always attractive. See, when we did questions that were masses and it was a gravitational field question, they always attracted each other. But now the charges are going to matter, whether they're plus or negatives, and you need to think about how that factors into how to build a question and get the answer. So I guess the first thing we need to do is not look at this example, but let's go back to the previous page, the start of this, and let's fill this page in together because there's a little bit of preliminary information here that you're going to need to do the questions. Now you will find a lot of these questions deal with electrons and protons, and you can look all this information up on internet if you wanted to, but let's fill this in together since you're here on the video, and you can write down some reference numbers right here. You're going to need these 4 values. You're going to need the charge on an electron. It's 1.6 times 10 to the negative 19, and the units on that are coulombs, which I'm not sure if you remember that yet, but the standard metric unit on charges, if you remember even back to grade 9, is coulombs. The mass of an electron, if you're in chemistry class this semester, you might have been using this. It's 9.11 times 10 to the negative 31 kilograms. The charge on a proton is exactly the same as the charge on an electron. It's just electrons are negative and protons are positive. But 1.6 times 10 to the negative 19 coulombs. And the mass on a proton, that's a number that is not used as frequently, but there are some questions that are going to have that number on them. It is 1.673 times 10 to the negative 27 kilograms. You can see that protons are a lot heavier than electrons. Electrons are to the negative 31. This is only negative 27. Some reference sheets won't have that 3 on there. It'll just say 1.67, but I find that that little 3 actually matters in some questions, so we'll use it. And really, the only thing that you need to know before you go into these questions, because these are reference values, you don't need to memorize them, but what you need to know, you've already learned many times, the law of electric charges. Opposite charges attract each other, and similar charges repel each other. And you need to know this because it is going to factor into how we get net answers in the end for these questions. Opposite charges attract, similar charges repel. Okay, so because this is online learning, we don't have the luxury of a classroom, we're not going to go through formula derivations. I'd like you to cut to the work as quickly as possible. So we need a formula for electric force. And the derivation of this formula is almost the same as the derivation for universal gravitation. And the formula looks very similar to universal gravitation. It's capital F for force equals a lowercase k Q1 times Q2 divided by the distance between them squared. So if you think about it, that looks very much like universal gravitation. But aside from having a capital G as a constant in the beginning, we have a new constant, lowercase k. And instead of masses, we have charges. Lowercase q is the variable for the charge on whatever object is in the question, and there will always be two objects. So, as usual, the left-hand side of this formula, capital F, don't leave it as a capital F only, because there are so many different kinds of forces. Let's put a little tiny E in the bottom corner here, just to indicate that this is electric force. And maybe I'll do this off to the side, just to indicate what this formula means. We're going to have, just like we did with masses, we're going to have two different charges, Q1, Q2, and a certain distance apart, measured center to center. And this is the formula that will give you the force of attraction between these charges, or the force of repulsion. Now the difference is K. K is a constant. It's a science constant that you can look up. It's totally, totally different than universal gravitation. K equals 9 times 10 to the 9. And it's not even negative 9. It's positive. 9 times 10 to the positive 9 newtons per meter squared over coulomb squared. This is on your... Well, I'm not actually sure that that's on your formula sheet, so that may be a value that you need to remember. 9 times 10 to the 9, and remember that it is not negative. The force of electric attraction and repulsion is so much stronger than the force of gravitation. Gravity is actually the weakest force of the fundamental forces. Electric attraction and electric repulsion is so much stronger, and that is where we get this positive 9, whereas the constant on universal gravitation was to the power of negative 11. So the work is very similar. In fact, if you look at this example here on the next page, if this example, this same diagram could have been used in universal gravitation. Those could have been 3 planets or 3 spherical masses a certain distance apart, and the question would be, in this case, it's what's the net force on Q2? If they were masses and it was gravity, we could have done this question weeks ago. So we're going to follow the same format. But now, what changes when they're charges instead? I drew this diagram just to match the question. And one thing you want to do when a diagram isn't given and you have to draw it yourself, you want to put the charges right here inside the circles. You want to know right away at the start of a question, what are the charges? Which ones are plus, which ones are negative? And make sure you have that in front of you. Because what you want to do, this is a really big hint for these questions. Before you start the question, before you start doing calculations, just look at the charges and ask yourself, what's going to happen to Q2? That's what this question's about. What's the net electric force on Q2? Well, let me cover up charge number 3 and let's just look at these two. So Q2 and Q1 are both positive. Like charges repel each other. So what's going to happen to Q2? Because of Q1, it is going to feel a force repelling it away from Q2. And I'm actually going to draw that right on here, right away. This is even before doing anything in the question. We're going to have a force between charge 1 and charge 2, and it's going to be in a direction that forces Q2 away from Q1. Now, if we do the same thing here and cover up this charge, and just look at these two, Q2 is positive, Q3 is negative. Opposites attract. So what's going to happen to Q2 because of the interaction with Q3? There's going to be an attraction. So Q2 is going to feel a force that tends to want to draw it toward Q3. And so that's going to be the force between 2 and 3. So all we need to do is figure out the values of those two forces. And if you're really keen on this and kind of paying attention, all we're going to do is we're going to figure out the force on those two values, and then we're just going to treat the question like it looks on this page. Just two arrows separated by an angle, and we're just going to put those forces together and figure out what the net force is. So if you ignore everything on the page except for what I've written in black marker, we could have done this question weeks and weeks and weeks ago if it was just this. Two forces, there they are, put them together and get a net force. So you see how easy this is. All we need to do is get the numerical values for those two forces. Now here's one other big hint. Do not use the signs when you do calculations. This diagram here uses the signs already. I drew this vector to the right because of the repulsion between those two positives, and I drew that vector attracting because of the attraction between the positive and the negative. So that's it. The signs are already considered in that diagram. We don't want to use plus and negatives when we actually do the calculations for the forces. So let's just do each one of these forces individually. I'll start with F1, 2, and only F1, 2, although you could build a giant calculation for this. Let's try and keep it easy and do it in small steps. So the force between 1 and 2 is going to be K, Q1, Q2, divided by the distance squared. And again, don't use signs. The charges do have a plus sign and a plus sign. Don't even put those in. So I'm going to write 9 times 10 to the 9 for the K constant. And that's Newton meters squared divided by coulombs squared. This is going to be a lot longer than the line that I drew here. So Q1, if you look in the question, is 4 times 10 to the negative 6 coulombs. Q2 is 6 times 10 to the negative 6 coulombs. And the distance between them is given as 0.25 meters, and that has to be squared. So don't worry about the fact that these numbers are all scientific notation. It doesn't change anything. Punch those numbers into your calculator the same as you normally would, and you will get an answer of 3.456. And it's not even in scientific, it doesn't even have exponents. It's 3.456 newtons. That's actually one of the reasons why you get charges in questions quite a bit that are to the negative 6. Because with the K constant multiplied into them, you'll get reasonably whole looking numbers if they give you charges that are to the negative 6. So 3.456. So all that tells us, going back to the diagram, is that this force, the force that's caused by the repulsion of Q1 and Q2, is 3.456. Now we're going to get this other force, the force between Q2 and Q3. It's probably a waste of time putting these details all on video because it's going to be this exact same formula here. In fact, maybe it would be easier if I just say, write out exactly the same thing. Write out the force formula, but change it to force 2 and 3. Let's do it together. I don't want anybody to get confused. So we're now going to calculate the force between 2 and 3. The formula is K, Q2 times Q3 divided by the distance between them squared. So, identical calculation. You really don't have to copy this down off the screen. You could probably do it faster yourself. 9 times 10 to the 9 Newton meters squared per coulomb squared. The charge is Q2. Now be careful not to confuse the charges. That's really important. 6 times 10 to the negative 6 coulombs. And Q3 was given as, on the page is given as negative 9 times 10 to the negative 6. But again, don't use the signs. I'm not putting the negative in there because the work with signs is already done. The distance is not the same. It's a little bit shorter, 0.2 meters this time, squared. If you're keen on units, you can see how this works out. There's 2 coulombs that cancel the coulomb squared. And on the bottom of this, there's a meter, which is going to get squared and become meters squared. which would cancel meters squared. And the only unit you have left is newtons for the force. So punch all that into your calculator, and you will get an answer of 12.15 newtons. So what the whole question has become, I don't even have to redraw the diagram with the charges, because what the whole question has become is you have a mass, and I'm even going to draw it as a little square just to really stress that this is now as easy as grade 11. You have a mass that is being forced to the right, 3.456, and it's being forced through attraction up on an angle with a value of 12.15 newtons. And the only angle that's given in the question is 30 degrees. So all we have to do to get the final answer here is put these forces together. At this point, it's not even an electrical question. Just put those two forces together however you prefer. You could probably do them tip to tail and make a non-right angle triangle and use Coase law. But remember, we don't like to do that in physics. I was telling you since the start of this course, the first thing you do in this question is anytime you have a vector on an angle, break it up into components. And because the 30 degrees is already given right here, I'm going to break it up into components up and to the right. So 12.15 sine of 30 degrees will be across from it, and 12.15 cos of 30 degrees will be right beside it. So if you work those two numbers out, 12.15 sine 30 will be 6.075 newtons, and 12.15 cos of 30 is 10.522. And I'm just keeping a couple of decimals to make it more accurate. So that completely eliminates this vector and represents it instead as those numbers. So now, just like earlier in the course, here's your answer. Put these vectors together, and it's much easier to put these together because they're all left, right, up, and down. Do it the same as you did in grade 11. Look in the up and down direction, and there's one vector, 10.522. And look in the left and right direction, and there's two vectors now going to the right. So add those up, and remember, you're not going to get directions on the final answer right unless you arrange them tip to tail. So I'm not just going to add these up and draw it on here any random way. I'm going to extend it right from the tip of this vector. So add those two together, and you'll have an answer of 9.531 newtons. So your final answer to this question will be this. It will be side C of that triangle. Always a right angle triangle, of course. And you need angles. You need to state in the end of these questions which direction they're in. So we're going to need this angle right in here. So do your standard work. This is a right angle triangle. Do Pythagorean theorem. C squared equals A squared plus B squared. Fill in these two values. 10.522 newtons squared plus 9.531 newtons squared. Take the root of that after you add them together, and you'll get a final answer of 14.2 newtons. So that is the magnitude of the answer. But we're also going to, I'm sorry, didn't realize I was off the screen there. We're also going to need the angle in this question. So looking back at the diagram, we've got an opposite side and an adjacent side to that angle. That's a tan relationship. I'm going to roughly write it down over here on the side, but hopefully you're making this a little bit neater and in order more. Tan of that angle will be 9.531 newtons divided by 10.522 newtons. The units will cancel out. Take the inverse tan, and you'll finish with 42.2 degrees. And as usual, you can't leave it as just an angle. You have to state that in a more appropriate format. And you're older now, you're into more advanced work, stop using north, south, east, and west. We will still occasionally, but here's a question where when it comes to electric field questions, it's very silly to have north, south, east, and west. But here's a question where that angle, you can see it right there, is up 42.2 degrees to the right. And I would write it like that instead. Up 42.2 degrees to the right. And of course there's a complementary version of that, but I'm not even going to write it down because I guess one other little thing you can add in for a hint is when you have two different ways of writing angles, you always go with the lowest version of writing it. I could write that angle as right, however many degrees up, the complementary of that, minus 90. I'm not even going to bother. That's the proper way to write it, and that would be the answer. So hopefully you understand this example. It's very sensible, and this is the kind of thing I like about grade 12. The work is very sensible. Sorry for the mess on this page. If you're still listening, there are 4 questions for homework. The first 2 questions are not a system of charges like this one. The first 2 questions only deal with this. It only deals with taking Coulomb's law and rearranging it to solve for other things in the formula. Question number 3 and question number 4 on the homework, they are systems of charges, but much easier than this one here. So we're going to break this into 2 days. We're going to do 1 day of homework where you've got 2 easy systems of charges to work on. And then tomorrow there won't be a new lesson tomorrow. We're going to do some other practice questions that are a little bit more, I don't want to say difficult because these questions aren't difficult, but a little bit more complicated because of angles and whatever else in the question. So that's all for today. Hopefully you totally understand this work, even just by one example, because you don't need several examples of this. You can actually go back to the gravitational fields and think of the same concepts that you were using then. It's just the formula is going to change. And really that's all it is. Change the formula and recognize that sometimes you have attraction and sometimes you have repulsion. And you have to set the vectors up correctly in the beginning. So that's what you do first. Before you do any calculations, draw a diagram and put those arrows on there in the directions that they're actually going to face so that you know right away in the beginning what it physically looks like.